Dear students, continuing with our lecture series on medicinal chemistry, this is our 10th lecture on medicinal chemistry and 4th lecture on cardiovascular drugs. In the present lecture, we will discuss about the synthesis of some common cardiovascular drugs. In the earlier lectures on cardiovascular drugs, in the first lecture, we have discussed about cardiac glycosides and antihypertensive drugs. In the second lecture on cardiovascular drugs, we have discussed about antiarrhythmic drugs. You can go through this lecture also. Then in the third lecture, we have discussed what are vasopressor drugs. Now, in the present lecture, we will discuss about the synthesis of some common cardiovascular drugs. And first, the most common one is amyl nitrite. The alkyl nitrites is the family to which this amyl nitrite belongs, and these alkyl nitrites, they can be prepared by a general method from the reaction of alcohols with nitrous acid, and this nitrous acid is in situ synthesized from the reaction of sodium nitrite and HCl. So when alcohols, they react with nitrous acid, these types of alkyl nitrites, they are prepared with the elimination of water, or you can say dehydration of alcohols with nitrites leads to the formation of alkyl nitrites. And in general, this reaction can be termed as a esterification reaction. And when this R group is an amyl group, the type of nitrite synthesized is amyl nitrite, which is used as a vasodilator for angina pectoris disease of the cardiovascular drug. Then next drug in this category is sorbitrate, which is very commonly used for heart failure, esophageal spasms, and to treat and prevent chest pain from not enough blood flow to the heart. So this sorbitrate, which is isosorbide dinitride, can be prepared starting from this polyhydroxyl called D-sorbitol. When D-sorbitol is treated under acidic conditions, it undergoes dehydration to give us in the first step 1,4-sorbitane. This 1,4-sorbitane, when further reacted under acidic conditions, then this is converted into isosorbide by double dehydration reaction. This first D-sorbitol undergoes one dehydration reaction to 1,4-sorbitane. Then another dehydration reaction will lead to the formation of isosorbide. And when this isosorbide is reacted with nitric acid, it can give us either 5-isosorbide mononitrate, where one of the hydroxyl groups present on the isosorbide undergo conversion into nitrite group, and this is called as mononitrate. Similarly, if both the hydroxyl groups, they are replaced by nitro group, then the sorbitrate is synthesized, which is 2,5-isosorbide dinitrate, and this compound is used as a cardiovascular drug, as I told you, for the heart failure or esophageal spasms or to treat and prevent chest pain. So this is very commonly used and important drug for cardiovascular diseases. Then other commonly used cardiovascular drug is diltiazem, and this diltiazem is basically a derivative of 1,5-benzothiazepine or heterocyclic compounds. The diltiazem is synthesized from the condensation of 4-methoxybenzaldehyde with alpha-chloromethyl acetate. So when these two substrates they are reacted under basic conditions, they are converted into these types of epoxides, esters through Darjan's reaction. And these epoxide esters, they, when reacted with 2-aminothiophenol, with the opening of this epoxide ring, lead to the formation of these types of methyl esters derivatives. And these methyl ester derivatives, when these are reacted with sodium hydroxide, then under acidic conditions, esters, they undergo hydrolysis, and we will get the corresponding carboxylic acids as the product. And a racemic mixture of these acid derivatives that is formed. Now, because the diltiazem, which is a drug, is an enantiomer, that means this racemic mixture is to be resolved into the isomer or enantiomer, which is required for the synthesis of diltiazem. So for that purpose, this racemic mixture of the carboxylic acid is resolved with this plus alpha phenyl ethylamine. So when this carboxylic acid is treated with alpha phenyl ethylamine, this gives us thirio plus 2-hydroxy 3-2-aminophenyl thio 3-4-methoxyphenyl propionic acid. So you will see this structure of the compound is same. Only thing is that the treatment with this phenylethylamine, optically active phenylethylamine, has resolved into two enantiomers, and this plus enantiomer is useful for the synthesis of the drug diltiazem. So when this plus enantiomer of the carboxylic acid is treated with acetic anhydride in dimethylformamide and pyridine, this undergoes condensation at these positions along with cyclization to give us 1,5-benzothiazepine ring. And then this 1,5-benzothiazepine ring derivative formed by this step then lead to the formation of the drug when this is alkylated with this N-dimethyl aminoethyl chloride. So this will undergo alkylation when this nitrogen will attack this carbon with elimination of halogen from air, and an alkylation will take place to give you diltiazem as the drug. And this diltiazem is very commonly used as a drug for cardiovascular. Then is Verapamil. Verapamil is again used in the form of injections for cardiovascular diseases, and this is synthesized from this 3,4-dimethoxyphenyl acetonitrile as the substrate. So this substrate undergoes two types of reactions, and this will lead to the formation of two derivatives which will combine with each other to give us the Verapamil drug. So basically these two reactions are in the first reaction, this 3,4-dimethoxyphenyl acetonitrile will undergo reduction, and this cyano group will undergo reduction to give us the primary amine function. So C triple bond N will be reduced to CH2NH2. Then this primary amine form will undergo alkylation with methyl iodide. So N methylation will take place to give us this alkylated compound, alkylated amine, and this alkylated amine will further undergo analkylation with this 1-chloro-3-bromopropane, and this 1-chloro-3-bromopropane, when reacted with this secondary amine, as you know, out of these two halogens, this bromo is a better leaving group. So that means nitrogen will attack this carbon to eliminate the bromo group, and analkylation will lead to the formation of this type of tertiamine having a chloride group at the terminal carbon. So this one derivative which is required for the synthesis of Verapamil is now ready through this functional group transformations of 3,4-dimethoxyphenyl acetonol. Similarly, another molecule of 3,4-dimethoxyphenyl acetonitrile, when this is reacted under drastic basic conditions, sodamide you know is a strong base. When this is reacted with this in presence of isopropyl chloride, this strong base, because of the presence of these electron withdrawing group, a carbanion will be generated at this carbon, and this carbanion will attack this carbon with the elimination of halogen atom. So carbon-carbon bond formation will take place, and we will get this type of cyano product, 2,3,4-dimethoxyphenyl 3-methyl butyronide. Then this butyronitrile will react with this N2,3,4-dimethoxyphenyl ethyl and 3-chloropropyl and methylamine. So this tertiamine halide will react with this butyronitrile derivative, and basically again here this hydrogen present at this carbon will be an SD carbon, and this will attack this carbon with the elimination of Cl from here and hydrogen from here, and a new carbon-carbon bond will form like this to give us a cardiovascular drug which is known as Verapamil, and this is the IUPAC name of this drug. Then another commonly used drug is methyl DOA. So methyl DOA again is synthesized from this 4-hydroxy-3-methoxyphenyl acetone as the starting material. And when this acetonitrile derivative is reacted with potassium cyanide in ammonium chloride, this undergoes addition of cyanide to this carbon of the carbonyl, followed by reaction with ammonium chloride to give you cyanoamine derivative. So this propanitrylamine is formed from the reaction of this phenylacetone derivative, and this gives us a racemic mixture of this propanitrile, which is resolved when this is resolved with this type of sulfonic acid. Camphor sulfonic acid is used for the resolving this cyanonitrile compound, which after hydrolysis will give us methyl dopa as the product, which is an optically active compound. So in this case, the L-alpha-aminonitrile is useful, which is formed from resolution, and that L-alpha-aminonitrile on hydrolysis with sulfuric acid will be converted into the corresponding carboxylic acid. Another method can also be used for the synthesis of methyl dopa. Here only difference between the starting material is that here 4-hydroxy was used, whereas here we are using 3,4-dimethoxyphenylacetone as the starting material. And instead of ammonium chloride, we are using ammonium carbonate here, and this reaction will convert this phenylacetone derivative into hydrantoin, which is hydrolyzed directly by barium hydroxide into the corresponding carboxylic acid. So only difference from this method is here we first synthesize the propanitrile, whereas here the hydrantoin directly gives us on hydrolysis with barium hydroxide the corresponding carboxylic acid. Now this racemic compound is resolved with the L isomer of camphor sulfonic acid, and treatment with 48% HBr will lead to the formation of methyl dopa. And this methyl dopa is used in various types of cardiovascular diseases. Then atenolol, which is one of the most commonly used antihypertensive agent. Atenolol, which is the first generation antihypertensive drug. This is synthesized from 4-hydroxyphenylacetic acid. When 4-hydroxyphenylacetic acid is reacted with methanol, we know alcohols react with carboxylic acid to give us the corresponding esters. So methyl ester of this acetic acid derivative is formed. Then this ester is converted into amide when this is reacted with aqueous ammonia. This methoxy group will be replaced by amino group. And then this estamide derivative reacts with epichlorohydrin in the presence of piperazine as the base. So this will help in the base catalyzed reaction of addition. This phenolic OH will act as an acidic hydrogen, and this will lead to nucleophilic substitution reaction at this carbon. So this oxygen will attack this carbon with the elimination of this halogen derivative. So nucleophilic substitution reaction will take place to give us this type of epoxide derivative, and then this epoxide ring will be opened when this is reacted with isopropylamine. So this nucleophilic pair of electron, they will help in attack of the nucleophile to this carbon with the opening of the ring, and one hydrogen from here will be shifted to this oxygen, and we will get atenolol as the product. So this is how atenolol, which is used as a common antihypertensive drug, can be synthesized from this type of acetic acid derivative. 4-hydroxyphenyl acetic acid can be converted into atenolol. Then is oxprenolone. The method is similar to what we have seen in the previous reaction, atenolol. So here only difference is that the phenolic derivative which was used in atenolol is replaced by this compound. 2-propyl 2-in-1-ol oxyphenol. This is reacted with epichlorohydrin. In the same way, this oxygen will attack this carbon with the elimination of this halogen. H from here, Cl from here will be eliminated, nucleophilic substitution reaction to give us this type of epoxide, and this epoxide in the same way as we have seen in the atenolol reacts with isopropylamine, again a nucleophilic addition reaction, and this will lead to the ring opening of this epoxide ring, will lead to the formation of oxprenolone, and this again is a commonly used drug for angina pain and anxiety, which is given to different patients of CVDs. These are the references which have been used for preparing this lecture. Thank you very much.